Okay, so let's continue the topic of definite integral and fundamental theorem of calculus. So after the examples of last class, we're going to state some rules, continuing to understand the concept of definite integral. And these rules are pretty related to the rules that you know for indefinite integration. Especially after having studied fundamental theorem, you realize that these two are related. And in order to define those rules, we have to define the functions that we work with. So, we'll define a couple functions, f and g, which are continuous on the interval ab. And the first rule is the so-called Can you guys keep quiet? So the first rule is the constant multiple rule. Of course, if you have the constant inside the integral, in the definite integral in this case, it comes out. K is assumed to be a constant. The second one is the sum rule, which if you have the integral of the sum of these two functions, is the sum of the integrals. So the integral from a to b of f of x dx from the integral plus the integral from a to b of g of x dx. The third one is the difference. It's almost the same. It's basically having a constant minus 1 multiplying. So the difference rule is integral from a to b of f of x minus g of x dx equal, so you split the difference, right? You have a difference of two functions, then the integral of this difference is the difference of the two integrals. X dx minus the integral from a to b g of x dx. So the fourth one, think about this for a second. So you're having the definite integral from a to a of f of x dx. What do you think this is? You start and you end at the same point. What should the result of this integral be? Have no length on your interval, right? So this has to be 0. Basically, it's an integral over an interval of length 0, so it cannot be anything else. The fifth rule is that if you have the integral now from b to a, f of x dx is equal to minus the integral from a to b of f of x dx. You want to understand how this works? Basically, it's because you're taking the integrals in, or the intervals in reverse order. So that's why you have the minus sign. Then you have another rule, which is called the subdivision rule. Integral from a to b of f of x dx. Then you have the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So basically, what you have is this interval a to b, and you have a point c in the middle. Okay. So this is what it's telling you. Let's say I compute the integral over this interval, right? So I can consider like first this part and then this other part. That's why you have c as a point between the two ends. Okay? So just to make a comment about this little geometric interpretation. So for the subdivision rule, the definite integral is computed over the interval AB, and it is the sum of the definite integrals over the subintervals, which first you have the subinterval from A to C, and then you have the subinterval from C to B. The same way we have it in the picture, right? Okay, so if you remember the rules for indefinite integrals, and you're aware of the fundamental theorem of calculus, these rules in a way are self-evident. It kind of makes sense. What you have to do now is to practice those rules. And that's why we have some examples into how to use these rules for definite integrals. So the first example have to let f and g be continuous functions. And actually, if you notice, look, in this example, you're not given information of the actual function f and g. You're only given the info of some integrals. And then you have to infer some other integral values. So there are continuous functions on the interval from -2 to 5. And these functions, the only thing I know is that the integral from -2 to 5 of f of x dx is equal to 3. The integral from -2 to 5 of g of x dx is equal to -4. And the integral from 3 to 5 of x dx is equal to 0. So yeah, this is a nice example actually, because the only thing that you need are the integral values to obtain the following quantities. So the quantities that you need to get, it's basically the evaluation of first the integral from -2 to 5 of the function 2f of x minus 3g of x dx. And so, look, you're a master of this, especially since we had the midterm yesterday, so you know these rules for indefinite integrals. So I'm pretty sure that for definite you're familiar. Basically, first we will take the difference. So the difference of these two functions integrated gives you the difference in the integrals. Integral from -2 to 5 of 2f of x dx. I'm going to go over baby steps. I know I could make 2 steps in once, but okay, we're studying this problem. Okay, this from -2 to 5 of 3g of x dx. So I took the difference between the two integrals. Then, of course, I can take out the constant terms. So this would be equal to, I will take the 2 out of the first one, 2 integral from -2 to 5 of f of x dx. Then I take out the 3, integral from -2 to 5 g of x dx. And the point is that I know the results of these two. Those were the givens, right? So it doesn't matter in a way, at least for this particular computation, that I should know the actual shape or definition of f and g. I just care about the values. So I can substitute. So this is 2. The value of this one was 3. And then you have -3. times minus 4. So you have 6 plus 12, 18. Okay, fair enough. With the info that you were given, you were able to compute. The second example is actually more interesting. I mean, this is basically a linearity thing. If you think about it when you're going to higher mathematics, well, basically you can think that the derivative and the integral are linear operators, okay? Because basically sum of the integral of the sums. You take the constant out. That is exactly what defines a linear operator or a linear function. So if you go into higher math, you will see that. The second thing is how to compute another integral, which is the integral from minus 2 to 3 of f of x dx. Now, what we know to make this computation is that the integral from minus 2 to 5 of f of x dx, remember, I have the interpretation, right? So this is minus 2, 5, and then I have a point 3 over here, okay? So in this case, what I'm going to do is precisely to split the interval. First, I go from minus 2 to 3 of this function, f of x dx, and then I go from 3 to 5 for this integral as well. Okay? Is this intuitive? Does it make sense? Do you guys see what I'm doing here? Basically, let's say I have this function, right? And I want to compute the area under the curve for this. Of course, the area under the curve can be computed by computing first this area and then this other area, and it's the same. Okay? I'm just splitting the integral. Because the one that I care is basically this one, and I have the information for some of them. Okay? So, well, this is intuitive, and we will just express what we want. So in that case, what you have is that the integral from minus 2 to 3 of f of x dx, so basically you pass to the other side, the integral from minus 2 to 5, so the computation, pass this one over here, f of x dx minus the integral from 3 to 5, f of x dx is equal to 3 minus 7, and you have minus 4. Okay, so we have a knowledge of these two, and we just did the computation. So this might become useful at some point. Basically, try to get familiar with the rules. The moral of the story is precisely that you didn't need actually the whole info about f and g. For these computations, you needed only the values of the integrals in order to obtain some other one. So the problem is chosen appropriately, but try to practice the rules. So the same way that substitution popped up in indefinite integration, it will come up in definite integrals. And so, in fact, in the definite integration, well, first of all, you have limits of integration. When you have the antiderivative and you have the difference, if you do substitution, you have to be careful into which limits you use. That can be a source of confusion, of a possible error, etc. So in any case, you have two options for these cases. When you're going to do substitution, so substituting in a definite integral, so you have kind of like two options, okay? Option one is to use substitution to find an antiderivative for f of x. That is one option. Basically, the same thing that we did before. After you do the substitution and you integrate it, you go back to x, and you're good to go. That is one option. The second option, though, it is to express the integrand and the differential dx in terms of u and du. So, okay, you do the first part of the substitution method, right? But you will also replace the limits of integration, which were originally a and b, and you will replace them with c, which is basically, let's say that g is the function that makes the substitution, okay? G of a and d equal to g of b. So of course, to be clear about it, you need to see an example, but in a way, it's kind of intuitive. Think about it for a second. You're going to evaluate a definite integral. You do a substitution, and you have basically a mapping between x and u. So in the limits, of course, you could go back again after the substitution to x and have the original limits, or just stay in the u variables and take the limits as the mappings between the endpoints of the interval and their values in the u's. Okay. So those are your two options. And in order to study this in more detail, let's do an example. That will clarify, I think, any works of concern. So you have example 5.3.7, which is the integral from 0 to 1 of 8x times x squared plus 1 cubed dx. Okay, before I proceed, you guys are familiar with this. The example is chosen appropriately, right? So which kind of substitution could I use given? Right, and what would you choose as u?
X squared plus 1.
Yeah, right. Why so? Okay, what is this? What is the derivative of u? If you propose this, right? So u is equal to x squared plus 1. Take the derivative, what do you get? 2. Right. So it's proportional to this, right? So you have a chosen problem where you have the u cubed and then something proportional to the derivative. So, I mean, it is given for you. Basically, it's trying to motivate you the intuition of like what to do. So yes, we will do that. First, we will be concerned with the indefinite integration, where we have a function u, which is equal to x squared plus 1. And okay, in this expression of the u dx, you have the u equal to 2x dx, right? So this is easy because, well, now if I consider, let's say, only the indefinite integral, 8x times x squared plus 1 cubed dx, indefinite for the moment. So if I do, well, basically I have, this would be u cubed, this is 4 times du, so basically there's a factor of 4, which relates the 2 to the 8, and this one is easy to do, right? So this is u to the 4th, in terms of the indefinite integration. So what we're using is, well, first we're doing indefinite integration, then we will use the fundamental theorem of calculus, since now we recognize an antiderivative. And so in order to stress these two possible options that I commented before, let's say that we follow option 1, right? So option 1 is to rewrite the antiderivative in terms of x, okay? Which means that basically we will do the substitution, we get the antiderivative, we have the difference, but we will go back to the x variables, okay? So in that case, we would have the integral from 0 to 1 of 8x times x squared plus 1 cubed dx. Let's go back, u to the 4th. Remember that u was equal to x squared plus 1, so this is equal to x squared plus 1 to the 4th power. And then the limits of integration for x were precisely 1 and 0, right? So do the substitution in your mind. Basically here you have, well, 1 plus 1 to the 4th, so 2 to the 4th, minus this would be 0, plus 1 to the 4th, so this is 1. So 2 to the 4th is 4 squared, so 4 times 4, which is 16, minus 1, 15, okay? And so, I'm sorry that it's becoming a little bit blurry. Is it happening often? No? Okay. So yeah, that's one way to do it. If you think about it, basically we did the substitution in the indefinite integration, then we went back to the original variables, and that's where we kept the original limits, and then we just did the computation, okay? So this is nothing. The second option, and so we're doing these two in order that you do not become confused eventually. So it's to try to be proper and avoid sources of confusion later. The second option is to find the values of u that correspond to x equal to 0 and to x equal to 1. So remembering that you have u equal to x squared plus 1, you remember that u at 0, you plug in x equals 0, you say you have 1, and then u at 1 is equal to 2. With these two, now you have enough info to do the computation. Because basically, okay, you have the integral from 0 to 1 of 8x, x squared plus 1 cubed dx. So basically, let's say do the substitution. Then you stay in the space of u. So you would have 4u cubed du. You change the limits. So basically 0 was mapped to 1. 1 was mapped to 2 in this case. And you can do the integration now with this limit. So this is u to the 4th as we knew before, but now with the limits 2 and 1 as we had them. So basically, if you think about it, this is like doing the job that later on we will do, right? Here you have everything in terms of x, and you will have to do a mapping, which is precisely this u, which is x squared plus 1, with the originals, which is something that we kind of like did before. So this is like saving this step in a way. And so what you have is 2 to the 4th minus 1 in this case, which we did the computation, and it was 15. So it's up to, I think in this case it's basically your own choice, because it really depends on how you think, okay? If you were even to ask me, I would say the first one is more algebraical and the second is geometrical. Because in the first one, what we do is a manipulation of variables. Basically, you go from x to u and then back to x and then do the computation. In the second, if you actually understand the intuition behind it, basically you're doing a mapping between the space of x and the space of u. And you stay in the space of u, and that's why you keep these variables as the limits of integration. So I'm not going to impose any choice that is yours, the one that you're most comfortable with. However, be careful when you do the substitution with limits of integration in order to keep a good result, okay? So, okay, you were presented the two options, and we will do now another example. But is the methodology clear on how we would do this kind of stuff? Yeah, is it clear? Okay. So let's do another example, and then we will continue. So the example is 5.3.8, which is the integral from 1/4 to 2 of natural log of x divided by x dx. Okay. Trying to follow the same approach. Let's say that you have that function. What is the u that you would choose? Think of it as an indefinite integral, right? And you were in the exam yesterday. What would be u? Well, you have a factor 1/x, right? So if you were to choose u as natural log of x, the derivative of natural log of x is 1/x. So again, you have one of these examples where you have hooked up the function and the derivative, okay? So again, in terms of expressing this as an indefinite integral, you make a choice of u, natural log of x, du equal to 1/x dx. Remember, this is the derivative. You can do the integration indefinite, so integral of natural log of x divided by x dx. If you want to put it in a more, in a nicer fashion, natural log of x, and then you have 1/x dx. So here you have your choice of u, and then you have du, right? Just the way we chose everything. So in this case, well, the integration is easy. It's basically u squared over 2. And if you were to substitute back again into x, you would have natural log of x squared divided by 2. This is up to the indefinite integration. I mean, it is clear now, right? Why they gave us this example. It's, by looking carefully at the integrand, you can realize what is your choice of u for the substitution method. Now, we can go back to the indefinite integration, sorry, to the definite integration. And so again, we have option 1, which is, now let's go back to the original integral from 1/4 to 2 of natural log of x divided by x dx. If we go back basically up to here, we have natural log of x squared divided by 2. This stuff will be evaluated between the limits of integration 2 and 1/4 because everything is expressed in terms of x. So you retain the original limits of integration. So, well, basically you only have to plug in. You have natural log of 2 squared divided by 2 minus natural log of 1/4. So this log is squared. Outside divided by 2, and then you take the difference, which, okay, well, if you do the computation with a calculator, you get something like this. So the important thing is the algebra at this point. In the second case, basically, well, you have to do this mapping between the x space and the u space, right? And so what you consider, again, as in the previous example, is the limits of integration, which are the endpoints of the interval. So for x equal to 1/4, u of 1/4 is equal to natural log of 1/4. Good. So for x equal to 2, u evaluated at 2 is natural log of 2. If you think about it, that kind of stuff appeared in the previous one. So the methods are equivalent, of course. It's basically at which step you do certain computations. But again, the one that you feel most comfortable with. So if you go back to the integral from 1/4 to 2 of natural log of x divided by x dx, then you do the integration. So we had basically, if you remember, the u du. So this is integral u du from natural log of 1/4 to natural log of 2. So you have again u squared over 2 from natural log of 2 to natural log of 1/4. And so, well, I mean the computation appears again the same. Natural log of 2 squared divided by 2 minus natural log of 1/4. This log squared divided by 2, which is the same stuff. So this is the same as this. But again, you have two equivalent methodologies. You can use them conveniently. It depends perhaps how complicated the problem is in order to decide which one to use, but essentially they're the same. So, having made this emphasis in terms of the substitution method for definite integrals, we will refine a couple concepts related to definite integrals and fundamental theorem of calculus. And one of them is the topic of net change. So, well, yeah, basically trying to relate these two. So the derivative is giving you a rate of change. It's basically the instantaneous velocity or the instantaneous rate of change of a given function. The integral can help you, if you integrate a given derivative, to find the total change between 2 points in the interval. If you think about it, well, basically if you integrate the velocity over time, you'll get the position. And if you do a definite integral, where you have the definite integral over 2 time points of the velocity over a space of time, you will get the distance traveled, which is precisely the difference between 2 positions. So try to express this more abstractly, and you get the following. So q prime of x is clearly the rate of change. And then, however, so that is the rate of change. It's like your velocity in a case, right? Q of b minus q of a is actually the net change, the total change, in q, in this quantity q, as x varies from x equal a to x equal b. But, yeah, this is a difference, of course. What this is trying to tell you is that if you had the information of the derivative of q, if you actually wanted to compute accurately the total change in going from a to b, you could do it by performing a definite integral of the derivative, and that is what we will do. So if q prime of x is continuous on the interval a, b, then the total change or net change in Q of x, as x varies from x equal a to x equal b, is given by, and now think about this for a second, right, which is related to what I told you. The difference, so the change Q of b minus Q of a, is the integral from a to b of Q prime of x dx. This is kind of, I mean, if it helps you even, like, I could write it some way that could be. This perhaps is more intuitive. Why so? You could actually think about this as a justification of the fundamental theorem in a way. So this is having the instantaneous rate of change, right? So this is telling you how much Q changes when you make a little change in x. Remember that the definite integral is basically the limit of this sum, where we compute for difference of intervals delta x, whatever is here, which is the Q dx. Loosely speaking, what I'm telling you is basically this is approximately delta Q divided by delta x, and this is approximately delta x. If I do the multiplication, I get delta Q. So this is the sum of the changes in delta Q, and you get the last value minus the first value. I will make a comment later on, because it's a way to understand the fundamental theorem of calculus, but it's kind of intuitive. I mean, you're keeping a track of the rate of change, and you also have how you change over the interval. So of course you're going to get the total difference. So in this case, to illustrate the example, we will do a particular function which will be the following. So let's say that you want to find the net change in cost. And of course, you're given the information such as the marginal cost, which you're told that it is 3 times Q minus 4 squared dollars per unit, when the level of production is Q units. So, when they talk to us about marginal cost, what we remember is that this is a derivative, and it's a rate of change. So what we want to obtain in the following statement, so statement is, by how much will the total manufacturing cost increase if the level of production is raised from 6 to 10 units. So what you're given is the marginal cost, which is the rate of change of the cost, and you're basically wanting to find the difference in the cost at 10 units minus the cost at 6. So again, the problems are chosen so that you develop your intuition in the topic, and well, you can go straight to the application of this concept. So the solution for this is basically that the C of Q is the total cost of producing Q units. So that means that this marginal cost is the function dc over dq, which is 3 times Q minus 4 squared, right? That is the marginal cost by definition, is this derivative. So dc over dq is the marginal cost. So what you want to find is the increase the cost, which is basically the difference between the cost at 10 units minus the cost at 6 units. So again, fundamental theorem of calculus, just apply with this particular example, the integral, definite integral from the endpoints of the derivative, which is dc over dq. Right? So you have your intuition that this is the limit of a sum where you have the delta q in this case, and then the function actually is approximately delta c over delta q. You kind of get the intuition that you have something what is called like a telescopic sum, and you will get basically the value at the last endpoint minus the value at the first endpoint. So in this case, you only have to plug in the function as you're given. So this is the integral from 6 to 10 of 3q minus 4 squared dq. Actually, in this case, I mean, formally speaking, you use substitution method, right? And the function u would be q minus 4, so you have 3u squared, which integrates to u cubed, and you could go back again. So we have actually skipped this step, which is basically this. So we did option 1. Think about it, u is equal to q minus 4, so you have integral 3u squared, so which is u cubed. You substitute back again, but you kept the original limits of integration. So you did all those steps in a single thing. In this case, it's simple because actually u is equal to q minus 4. It's a linear function and you have a constant, but the constant disappears when you take the derivative. That's why the u is equal to dq. Just trying to develop the intuition. So you could plug in these values, and then this is equal to 10 minus 4. So you evaluate cubed minus 6 minus 4 cubed. So you take 6 cubed minus 2 cubed. You take this is basically 36 multiplied by 6, which is 216, and then minus 8, which is 2 cubed, and then the answer would be 208. Okay? But again, the problem is chosen so that everything is perfect in a way, right? Because you were given the derivative by the marginal cost. So of course you have to integrate it, obtain the difference in the values between the right endpoint and the left endpoint. Okay, the application of this was straightforward. There is another example which comes from now chemistry, where in example 5.3.10, you have to find the total change in protein mass. So the statement of the problem is the following. Protein with mass m, the units of the mass are in grams, disintegrates into amino acids at a rate given by, and then you have dm over dt. So of course this is the rate of change of the mass with respect to time, and the function is minus 30 divided by t plus 3 squared, and the units are grams per hour. Okay, so you're making your choice of units of time as well. So the question is, what is the net change in mass of the protein during the first two hours? Okay, so you want the total change again. In this case, well, again, we will explain a little bit more about the intuition of this, right? So for the solution, what you want to know is the total change, the net change, which is the mass at 2 hours minus the mass at the initial time, which is 0. So it's the integral from 0 to 2 of dm dt. Before I continue, do you find it intuitive why we get this difference by computing this? Is it kind of good? Yeah, right. I mean, if you're computing basically the difference by means of the derivative, if you're not clear about it, think about it as a sum. And again, you have delta m over delta t, and then you have delta t. So it kind of collapses, and you get only the first and the last values. So maybe I will make a point at the end. But okay. In this case, you have to plug in the function that you're given. So this is minus 30 divided by t plus 3 squared dt. So you have the integral from, well, actually what you could do is to use the substitution method in this case, where you're given the quantity, u equal to t plus 3. Again, it's a linear function, so the u is equal to the t. If you do the mapping, u of 0 is equal to 3, u of 2 is equal to 5, which are, you're taking the endpoints in the x space from 0 to 2 to the endpoints in the u space, which are 3 to 5, which is what we're going to do. So we're doing a substitution method. If you think about it, where we have now the limits of integration as of here, and it goes from 3 to 5 in the u variable. So you have minus 30, and then u to the minus 2. Think about it. This is u squared in the denominator, so it's u to the minus 2 du. If you do the, well, you will have 30 u to the minus 1 from 5 to 3. Think about it for a second. The antiderivative would be minus u to the minus 1, but you have a minus sign there, so you incorporate it and you're clean. And then this would be equal to 30, and just evaluate basically 1 over 5 minus 1 over 3. You can actually do the multiplication on this side, which is 6 minus and then 10, and then this is equal to minus 4. Okay, we have a convenient fact. So yeah, they used like the option 2 in this case, and the final result would be that m of 2 minus m of 0 is equal to minus 4 in the units of grams. So it means that the mass has decreased, right? Because you have basically a negative difference. So this is the net decrease over the first 2 hours. Remember that the time was in hours. Okay? So last part is, well, look, the book is doing this. The way it tries to present the concept of definite integral is by introducing how to compute the area under a curve, which is actually a very reasonable way to introducing it. It's actually the usual way it's introduced. Then, basically, okay, we stated the fundamental theorem of calculus. I didn't do any formal proof. A formal proof as in mathematics is beyond the scope of this course, but the book is trying to do a justification of why it is true. So, in the last part, you have area justification of the fundamental theorem of calculus. And so, you have the following information, which is that you assume that you have a function which is non-negative, so it's greater or equal to 0, and you kind of already know that the integral from a to b of f of x dx is the area under the curve y equal to f of x over the interval ab, and for x fixed, which is between a and b, you're going to define a function. Actually, in probability, this kind of stuff is common, by the way. So I would keep an eye if you continue along that line. So you let a function a of x denote the area under the curve y equal to f of x, but now it's over the interval ax. So you notice the difference? Before you had the domain ab, right? And you had the area over the whole, well, below the curve over the whole domain. Now what you're doing is you choose a value of x in the interval, and you compute only the area between a and x. It's different, right? It's less area, in a way. So, In this case, you have the difference quotient of this function, a of x, is a of x plus h minus a of x divided by h. So, I mean, this is related to the derivative, right? In fact, this is what you take in the limit to get the derivative. So, just to give some intuition, if you think about of the difference, a of x plus h minus a of x, this is the area under the curve between x and x plus h. Now, for h small, well, that area is approximately the area of the rectangle with height f of x and width h. So basically, what you have, I will do a drawing in a second, but if you compute the difference in the areas between these two, a of x plus h minus a of x, this is approximately f of x times h. So, if you do some manipulation, basically this ratio, which in the limit is the derivative, is approximately f of x. Now let me do the picture. So in the picture, you have this function, you have a curve, you have basically a, b, you have, well, x, and you have x plus h, okay? And again, this area, formally speaking, the difference in ax plus h minus a of x is the area over here, right? And now, approximately, we again approximate the area by these bars, and it's a bar of width h and height f of x, where this is the point x, f of x, and this is the curve y equal to f of x. So here we have this, okay? Now, this is an approximation, but what we know is that we converge to an equality when we take the limit. So, the approximate error approaches 0 as h goes to 0, of course. I mean, if I make this subinterval smaller and smaller, of course, it is approximately in the area below the curve in a better fashion. So, what we want, or what we get, is that the limit as h approaches 0 of this, ax plus h minus a of x divided by h is equal to f of x. Now, this by definition is actually the derivative. So, if you think about it, a prime of x is equal to the limit as h approaches 0 of a of x plus h minus a of x divided by h, which was equal to. So, well, this is an intuition of why you get the fundamental theorem. You can also have some intuition in terms of this quotient difference. There is also one last comment, which is that, let's say, f of x is any other antiderivative of f. So in that case, what you know is that they're only separated by a constant. And since a is the area under the curve between A and X, what you know is that A evaluated at A is 0 because the length of the interval is 0, and this is also equal to f of A plus C. So that means that C is equal to minus f of A. And basically what you have is that A of B is equal to f of B plus C, which is equal to f of B minus f of A, that you know by plugging in this value, and then you have the area, which is the total area. So, well, we will continue in the next class, this concept. We're almost done. I just, we'll summarize some points later, but this would be a justification of the fundamental theorem in terms of areas.